Alright, when we look at 3.6, we're talking about the derivatives of logarithms and inverse trig functions. So let's look at the derivatives for logs. We know that the derivative of ln of x, or log base e of ln of x, is just 1 over x. And the derivative of ln of u, meaning if you've got a composite function, derivative of ln of u is 1 over u times u prime. And derivative of ln of g, same idea, equals 1 over g times g prime. The absolute value, ln of the absolute value of x is 1 over x, and I'll show you how that's proved later on. But if you don't have base e, you got base b, some base other than e, it's not just 1 over x, it's 1 over x times ln of that base, whatever that base is. And our trig functions are these ones here. These are the inverse trig functions. I won't expect you to memorize those. You'll be given those if I ever ask you a question like that on a test. And so here's your different derivatives. So let's take the derivative of ln of 3x to the third plus 1. So you'd expect it to be 1 over x to the third plus 1 times the derivative of x to the third plus 1. And that's what it is. And these are the same rules that we had before. Example 2, what's the derivative of ln of sine? It's 1 over sine times the derivative of sine, which is cosine. The square root of ln of x, that's the chain rule, because you got ln of x all raised to the 1/2, so you bring the 1/2 out front and subtract 1 from the exponent. And now you got to also follow that with the derivative of ln of x, which we know is just 1 over x. Here, this is base 10 now, so when we take the derivative, we're going to get a ln of 10 in here. So you get 1 over this guy times ln of 10 times the derivative of the 2 plus sine x, which is just cosine x. Here, you take the derivative of ln of this, it's 1 over that complicated guy times the derivative of that complicated guy, which is when you flip this and multiply times the top, you get that. And when you take the derivative of this, you have the quotient rule, and it's complicated, and you get it eventually simplified. At some point, you have to multiply top and bottom by 2 to get rid of the 1/2 in the fractional exponent, and you combine like terms, and you finally get to there. There's another way you can do this same problem. Is if they're asking you to take the derivative of ln of x plus 1 over square root of x minus 2, you can use the log rules. Ln of a fraction is the ln of the top subtract ln of the bottom. And if the bottom is raised to the 1/2 power, which is what the square root is, you can bring the 1/2 out front. So the derivative of this is also the derivative of this. And the derivative of this is a lot easier to figure out. It's just 1 over x times, it's 1 over x times 1 minus 1/2 times 1 over x minus 2 times 1. And there you go. It's a lot faster if you rewrite it using log rules. This one, to make a long story short, is basically finding out what's the derivative of ln of absolute value of x, and you find it's 1 over x. You can look through that if you want. What's the derivative of y equals this? Well, if you write this rewrite using logs, you take the natural log of both sides. That allows you to break this guy up into a lot of smaller pieces. It's ln of the top subtract ln of the bottom. And the top is two things multiplied, so they break up into addition. And the 3/4 comes out front, and the 1/2 comes out front. And for here, the 5 is going to come out front. And so now when you take the derivative of each one of these guys, you get 3/4 times 1 over x times 1. You get 1/2 times 1 over x squared plus 1 times the derivative of that, which is 2x. Minus 5 times 1 over 3x plus 2 times the derivative of 3x plus 2, which is 3. And you can simplify all that down. Now, you got on the left, when you took the derivative of ln of y, you get 1 over y prime. Because we're doing implicit, when you take the derivative of y, you get a y prime there. Now, if you solve that for y prime, you have to multiply both sides by y, and you get this. Now, remember what y equals. Y equals this guy here. So take that and put it in place of what y is. And then you've got your answer. All right? So steps for logarithmic differentiation is take the logs of both sides and then use the log rules to expand it. Then you do implicit differentiation and you solve your result for y prime and replace y with f. Alright. Now they talk about you have to be careful about the difference between the power rule, where the base is a variable and the exponent is constant, and the rules for differentiating exponential functions, where the base is a constant and the exponent is variable. Alright. So they show the four different possibilities. If you got a constant base and a constant exponent like b to some number, like, I don't know, 5 to the second, that's a constant, and the derivative of a constant is just 0. Now if you got some function raised to an exponent, that's the chain rule. You know, the power rule with the chain rule, you bring the n out front and subtract 1, and then you take the derivative of what's inside. Now here, this is the logarithmic rule, where you take the derivative of b to a function raised to a functional power. It's b to that functional power times ln of b, your base b, times the derivative of the exponential function. And now if you want to take derivative of a variable base and variable exponent, f and g, you might want to use implicit logarithmic differentiation like we're about to do here. So if you got y equals x to the square root of x, take the natural log of both sides, and you can bring the exponent out front. And now take the implicit differentiation of everything. And then you want to solve it for y, or y prime. And then replace y with what y equals, okay? And now you've got it. Y prime equals this whole thing right here. Now there's another way you can do it. Now we can use this idea that if you got something like z to the fifth, you can write it as e raised to the ln of z to the fifth. This and this are both equal. And you can bring the 5 out front, and so you got e to the 5 ln of x. That's what they're doing here. They're taking they're rewriting this as e to the ln of x to the square root of x, and they're bringing the square root of x out front. So now if you get this guy equals this, when you go to take the derivative of the left-hand side, you can rewrite it in terms of the right-hand side, since we showed they're equal. And now when you take the derivative of this, you get the same item back times the derivative of the exponent. And derivative of the exponent is the product rule, and when you combine like terms and simplify, you get this guy here. They talk about showing how they find the number e. Well, the number e is found two different ways. You can analyze 1 plus x raised to the 1 over x as x gets smaller and smaller, or you can analyze 1 plus 1 over n raised to the n, where n goes off to infinity. Either one will get you e. But in this page, they talk about how they can prove that limit equals e. So they start out with f equals ln of x, and they take the derivative, which is 1 over x. And so if you plug in a 1 here, you just get 1. Now they say, what's f prime? Well, they do the 1 plus h minus 1 all over h, and they simplify it down. And now this part here, ln minus ln, that's subtraction. You can write it as division, and dividing by 1, it doesn't change it. And then the 1 over x, this is 1 over x here, that's brought into the exponent, and now you've got this guy right here. Now because f prime of 1 equals 1, and this guy equals the same thing, we have this guy equals 1, and thus the limit of this guy equals e to the ln of 1 plus x, 1 over x, which is e to the limit of the exponent, which we now know is 1, so e to the 1 equals e. It's another way of showing what e is. Here they talk about how they calculate the derivatives of the inverse functions. You can look through this if you want. It talks about the derivative of sine inverse and the derivative of tangent inverse. But here are the 6 basic rules for the inverse functions. You don't have to memorize these. I will provide those for you. Now what if they ask you to take sine of 1 over sine inverse? Well, don't confuse the negative 1 here, which is notation for sine inverse, with a negative 1 in the exponent for an exponent, a negative 1 exponent. That's different. We rewrite this since it is all to the first power, if you bring it into the exponent, it makes it to the negative 1 power. And now when you take the derivative, you bring the negative 1 out front and subtract 1, and you follow it with the derivative of what's inside. Well, the derivative of the sine inverse is 1 over 1 minus x square rooted, and so you get this guy here. Now what is, if f equals x arctan square root of x, that's x tan inverse of square root of x. Arctan and tan inverse mean the same thing. So how do you take the derivative of this? You got to use the product rule. So you get the first guy times the derivative of that, which we know is 1 over 1 plus x squared. And remember, the x that you're putting in place is really square root of x. So it's 1 over 1 plus square root of x squared times the derivative of the square root of x, plus arctan of x, unchanged, times the derivative of 1 of x, which is 1. And now you can simplify that guy down to here, and this guy just becomes arctan, and that's your answer. Now if you want to differentiate g equals secant, inverse secant of x squared, it's 1 over x square root of x squared minus 1. But instead of x, you're plugging in x squared, so it's 1 over x squared, square root of x squared, squared minus 1, followed by the derivative of x squared, which is just 2x. And that simplifies down to what you got there.